as you see, here I have a list of failures or failure modes, and that's really what you call them or refer to. I mean, it doesn't really matter as long as you know what we're talking about, but the concepts of failure or failure modes, I would say they're equally often used. But it is ultimately the same thing. Those are the random events. So what we're going to do is to create those, add those into OPUS Suite. So I'll copy the identifiers for the failures. So copy. Going back to OPUS 10 here, and there is a category called failures here. So, and then often it's like this, that the definition table, as I mentioned before, it's the same name as the the element. So if we are to model failures, the name of the table is failure. If we are to define new items, the name is item. And if we are to define a new product variant, the name of the table is product variant. I guess it makes sense. So in the table called failure, as you see here, I'll paste the identifiers. There they are. So we get the list of failures here. There might be descriptions of them, but we don't have that. But we will, however, connect them to the item identifiers in this case. And if you will recall from the presentation, this means that those events will happen to the hardware items, no matter where those items are installed. So if we would have had multiple configurations of the helicopter and the same item would be in a different variant, this failure would have been applicable for that variant as well. And this is how you see, if you remember, you can give a breakdown element identifier, and you can give an item identifier, or a combination. They are both yellow, but it doesn't mean that we have to give both in this case, but we have to give at least one of them, because otherwise you get an error later on. But that's what we did here. And next column in this table, as you see on the right here, it's probably impossible to read, but it says repairable. So it means that whenever this failure happens, can we actually repair the item or not? In this first example, we say we'll leave this empty, meaning that we'll take this default value standing here. So it's a Y for yes, but of course I can select yes or no for each of those failure identifiers. And no means that when this event happens, the associated item cannot be repaired. So we need to buy a new one. So it will trigger that we discard the item and reorder a new one. So that's extension of the model. But for now, we are only looking at repairable items. But I think it's of interest to understand that it's possible here to say that this failure mode leads to that we need to discard the item or not. But here, as again, they are all repairables. Next step is to give some more information about the failures here. So we want to give the rates or how often these failures happens. And this table is called failure rate. And I paste the identifiers here. Again, our failures. And here comes this operation parameter. And that's what I talked about before, that we can give this for the number of per calendar hour or per operating hour, or we can also define our own operation parameters, such as kilometers, landings, takeoffs, firings, or whatever you want. But for this example, we're working with operating hours, so we want to give the data per operating hour. And here comes the actual data column in this field here, which is expressed as a failure rate. And here, when you have the brackets like this, it says that's sort of the unit of this value. And so the unit here is 1 per million operating identifier. And the operating identifier is the column to the left, which here is the operating hours. So this is the number of failures per million operating hours. It's kind of a standard way of giving this, but I mean, a rate would be, you know, the inverse, or 1 divided with the mean time between failure. So, which is also a common way of representing failures. But here we use this as the failure rates, so the number of failures per million operating hours. In the Excel file, we have this represented here. So I just copy that data, I'll paste it into OPUS. And again, we can see the number of decimals, etc. You can adjust that. Remember, right click and you have the column format that you can adjust. So now we've defined the failure, we have connected it to the items, and we have added the failure rates. Next step here is to define what are we going to do when those failure happens. So we will need to add tasks, which, as you recall from the PowerPoint, we have the smallest building block of the main description of maintenance are the tasks. So next category of tables called maintenance here, we have the table called task. Again, it's a definition table where we define this task. Okay, so looking in the Excel file, we have 2 tasks here. Scroll a little bit here. Zoom, maybe zoom. No. There we go. Okay, so we have 2 tasks. It's one remove, replace. Just make it bigger. It's the remove and replace of items. That's one task, because when a failure occurs, we most often need to replace the part to be able to fix it. And if it's, I mean, that's why we have spare parts, right? Because if we take out the faulty one, we can replace it with a new or a fresh one that is working, while the other one is repaired. Anyway, so that's one task. And then we also need to define the reparation of the item. So we have another task called repair item. So I'll copy those 2, and I'll paste them here in the task table. So remove, replace item, repair item. And here's you see again the yellow column called type. It's an important parameter and important to understand the difference. So it's simply different types of the task. And the default value is, it says here again, it says rectify. Rectify means that we fix the item, or we repair the item. It's a way of getting it nice and shiny again. Okay, so that's one type. But if I click the arrow here, we can see that we have some different type of tasks that we can define. And the 2 most common ones is, as I said, the rectify one, but the other one is the replace type. And this first task defined here, it is actually a replace task. So it's it's a time it takes to remove and refit the item and this is into the system. And this is also important. This is because I got a question about this the other day as well. So the replace task is the sum of the time it takes to remove and replace the item. So they are aggregated into one task. And of course, we can over here also give the duration of these tasks. If you don't like the order in which those columns appears, you can always drag and drop columns like this. So you can rearrange your data in a way that fits you. So if you want to have the title and duration next to each other, we can just, as you saw, just drag and drop those. Okay, and the other one, the repair item, it is obviously it's the actual repair of the item, so it's the type is rectified. Now I can select, since the default value is rectified, that means that I don't have to specify this, because it will always take the default value. But for clarity, I can select rectify here anyway. And then we have the duration here, and so we need to specify how long time it takes to perform the tasks. And going back to the Excel file, we see that we have task duration here of 4 hours for the replacement and 730 hours, which is equal to 1 month for the reparation. Okay, so 4 hours and 730 hours. So going back to OPUS, here is something really important that it's easy to miss. But I said that we have the default values within those greater than or less than signs, but we also have the unit of the measure. And here it says days. If I type 4 here now, this will make OPUS think that it takes 4 days to remove and replace one item. That's a quite long time and will give you really poor availability of the systems and probably not real work case. So what I need to do is to right click this column and I go to the column format and I can change the unit at the bottom. Before we were looking at the decimals here, but now I can change the unit. I don't want it to be days. Of course I can express it as 1/6 out of a day, which is 24 hours, but it's easier to change the unit to hours here. So give it that hours instead. You see what happened now, that's 96 hours. Well, that's not right. So let's delete that value and type 4 instead. And then we had the reparation, it was here, 730 hours, or which is 1 month, but represented in hours. But that's a sort of a, we say, a hole that it's easy to fall into, that you miss the unit of the column, and especially when it comes to hours. Otherwise, it's seldom a problem, but it's not a problem here either. But I just want you to know that it's important to get the right unit. Okay. So that's the task. And now, of course, we need to link those tasks to the events. So looking in the category called failures, there is a table called repair, right? And here we can link or connect each of the failure identifiers to a task, or if you recall from the presentation, we can use task packages or maintenance activities as well. But here we only have one single task for repairing the items. I'm kind of lazy, so I don't want to type all the 8 failure identifiers, so I'll copy them instead, going back to the repair table and paste them here. So I don't have to type them. And then this is, so what happens when those happen? What do we need to do when those failure occurs? Well, we can select from the repairs that we have here, and yeah, those ones were already in the model. We don't have to think about them right now, but we take the reparation of the item. That was the task that we wanted to perform for fixing or rectifying or repairing the item. And we say that it's 730 hours for all items, meaning that we can actually use the same task identifier for all failures. Of course, if you have different repair times or different tasks for different failures, you simply create additional tasks and connect them to the correct failure identifier in this table. But as a first example, it's 1 month reparation for all items, so we give the same task here. The other thing, this is also, I forgot to mention, you see what happened now was that those nodes here were white before for the items. But now, when I made them repairable, because I assigned a task to them here, they got yellow. But if it would have been that one of the failures here was not repairable, that's a no here. You remember, we have the repairable column in the failure table specifying whether it's possible to repair it or not. If I said no there, what happened was that the corresponding item, the combustion module here, it turned blue in this breakdown structure. And that means that this is a way of helping our users to understand the model they're building. So by using coloring codes, it will be more clear what items, or if you're doing anything wrong also. So it's a way of trying to help the users to understand the input data. Okay, I'll remove that again because it is so far we will see this as repairable. So I remove it, and it's yellow again. And the other task that we created was the replacement of the items. This goes into a different table, and that's because the replacement is related to the structure of the system. That means that we also need to define it in the same table as where we describe the structure. And the structure is described in the table called product breakdown. If you recall, this is where we added the breakdown elements to the variants and so on. And here you also see this column on the right here, replacement task identifier. The first row is defining this subsystem of the engine, which doesn't have any realization, it doesn't have any hardware items, so there is nothing to replace on that for this element. However, the rest of the list are our 8 items, so this is where we're going to give that replacement task that we defined previously. So it's here, remove replace item. It's a little bit small, but what I'm going to do is I'm going to remove the descriptions from this. I right click in the tree here and I deselect the descriptions in the trees. It's a little bit more narrow, maybe. Anyway, you see it here, this there's the remove replace of the items, and it's the same task again for all, so I do the fill down. But if the replacement tasks are different, just as for the repair, if it's different for different items, maybe it's more complex to remove the module rather than the gearbox, you know. That means that I can create separate tasks for the replacement for the different items, and of course then also give separate durations or turnaround times, and as well as costs and other additional information. But here again, it's the 4 hours replacement for all items, so that's why we used the same task identifier for the replacement. Okay, so that was the failures, right? The events, and it was the task, the maintenance, and we connected it to the product breakdown. So that was that step. Now we'll move on to the next one. Continue here, just few slides on that one, and. Yeah, we talked about this before as well, that it's important to sort of start simple when you model, and then you can gradually refine the model. So there can be a lot of value getting out from a simple model or like, you know, basic model, but then you gradually refine and add data as you get it and more details. So yeah, here we sort of go from an aircraft to the first level, and then we continue maybe with items, and then we continue with next level, etc. So until we have the full breakdown structure. Yeah. Anyway, so far we've been looking at this section of the input with concerning the RAM properties of the helicopter. As you know, we described the product and the elements and items and the failure tendencies and the repair tasks and so on. But next part to look at is the actual support organization. Okay, there are some different building blocks again in also here for this part of the model. And first of all, we have what we call stations. So stations is the actual the position within the support organization. Locations, see them as geographical locations. Your workshops, your operational sites, your warehouses, depots, whatever you might have. They can be of different types, those stations. So, and it's again color-coded in OPUS. So a yellow one is called a workshop. At the workshops, we are able to perform maintenance but we cannot store any spare parts. At the green ones, which are called the depots, we can both store spare parts and perform maintenance. Then we have the type called store, where we cannot perform maintenance, but we can do sparing. And then at last we have the operational sites, where we can only deploy systems, but we cannot perform any repair, and we cannot store any items. And so now you think, why do you have a lot of these things? Like complex, why do we need different types of stations? But it's actually pretty good, because it makes you able to I mean, otherwise you would always, if we're doing spare part optimization, it is sometimes beneficial to have spare parts at certain locations. But if that's not possible, if it's not a storage location, we don't want to have the results telling us to put spare parts at this location. So that's why it's good to have those types. And then, of course, we need to build the structure of the support organization again, just as for the product and the product breakdown. We use like a parent-child relationship to build up this structure. And here we see, typically you have at the top, you have the workshop levels. This is, you're not, let's say that this is the manufacturer, the OEMs or something like that. We're not storing anything here if we are the user of the systems. But we send stuff here for repair. And then we have a depot, maybe a central depot, serving the entire country or larger regions. Then we might have regional stores, maybe, yeah, you know, like we did in the EVO example yesterday, we have like a north location and a south location in our country, for example. And then there might be operational sites that are supported by those stores. Here in this example, we have one operational site supported by this store, and over here we might have two different sites that are supported by the other store. And why do we do that? Well, that's because there might be different transportation times, because you can define the times to send stuff between those locations in the model as well. So maybe this site Y here is really close to this store, so it only takes 2 hours to get a spare part down. But then we have another store which is also supported by this one, but it takes maybe 2 days or 48 hours to send the spares there. So it's flexible, and you can define it as according to your reality. And next part of this is how this relates to the maintenance. And concept of maintenance levels is something that we've also introduced in the model, because making it more applicable to real life. Often there are different naming of this, I know, but kind of standard to talk about operational levels. So we have the O level, meaning that we can perform O level tasks here. Then we have some kind of intermediate level where we can do the I level tasks. And then we have like a depot level or a D level where we can do the really complex stuff. Those in the model, the levels are inclusive, which means that you can always do something that is of a lower rank. So at D level, in this case, we can also do I level and O level stuff. So yeah, okay, let's add this to model. Okay, so what we have in this support organization, as you see, it says support organization up here. So this is the part of the input where we illustrate our stations and the support organization. We have one box for a base called Alpha, and we have one box called Central. And here again, you see the colors, just as from the presentation, representing the different type of these stations. So those stations are, and if you can guess, there is a category called organization, and the name of the table would be station. Yeah. Again, that's the definition table. This is where we define those objects. So it's the same name as the element itself. It's called station. And here you see the two ones, base alpha and central. And alpha is of the type OP, so operational. If I click the arrow here, you see those 4 types that I showed you before. And while the central, it has no value, so it gets the default value here of that OP. But we want to, what we're going to do is to just add another station here. So we want to add a station called beta. A small tip that is nice. I like to sort of organize the data in a table in a way that makes it easy to follow. So maybe I want to list my operational bases first. So that means that I want to get another row in between those two ones. So either you can right click here, you can do insert row like this. And you saw that there's always a shortcut command. So it says Control I. Also, same as for Excel, you have insert row, Control I. Anyway, I want to do a base beta here, and it popped up immediately here, but it got green compared to the alpha. Why? Well, it's type, but again, the color is representing the type of the station. I want to change this from depot to operational. So here, from base beta, I click this one, select operation. And you see, it turned, I don't know what that color is, maybe red. Let's call it red. Right. Now, next step is, of course, to create the levels of the organization here, so how they relate to each other. Then we go to the table called station structure. So it's just below here. And here we have, again, this parent-child relationship, where we give the station, and here is the mother station identifier. And, okay, so for base alpha, selected here in the list, the parent would be the central station, like this. And now you saw how it sort of popped down here. We got a link between those stations. And it ended up below because this is central is the parent. But then, of course, we need to do the same thing for the beta station. So I select beta with the parent central. Now we've created this. Make it a little bigger. Now we created the hierarchy or the structure of our support organization. So fairly simple. Saving. And of course, we also need to add, let's see. Wow. Turn off yeah. Where are we? We are here. Oh, we're just scrolling a little bit in this Pixel 5 here. So you see what I'm doing. So here we have the support organization is defined here, where we have the station and the mother station, and here comes the transportation times. Transportation times is simply the time it takes to send something between two stations in this organization, because of course that is going to be an important fact when we do this analysis. I've been talking a lot about the support response. So how can the logistics support organization respond to the needs from the operations of the system? And if we have long transportation times, the system will be waiting, it will be unavailable for a longer period, which makes it makes us able to produce less hours of operations. So the transportation time is important, and we said that sending to the mother station, let's see, transport time to mother station was 168 and 200 hours. Paste it here, and the time from mother station is 8 and 16. And it might be, now you wonder why do you have such a big difference here, but it's might be that you pay more for the transportation sending stuff down because it's a rush to get the items down to the systems. because we don't want the system to wait for too long. So we might pay more. We have a different method of sending stuff down. But however, sending stuff up to the repair might be not as important, or we select to pay less for this. Yeah, awesome. Exactly. So that's why we can give different times for sending stuff up and down. And of course, this is also represented graphically up here. So if I point on the line between the alpha base and the central, it's really hard to read, I know, but it says that the time to molestation is 168 hours, time from molestation is 8 hours. So far we haven't added any costs, but we can also relate costs to those transportations as well, both up and down. Yes, so that concludes how we build the support organization. So anyway, we continue where we were, and we continue building this first model. And keep in mind this, that we started off with this knowing some parts of the basics, and then we need to know more, so be able to calculate the mean logistic delay times for the systems. We need to know what happens further back in the support organization, which we started to build, but that's what we did before lunch. And now we move into the requirements, the operational plans and operational requirements that we're looking at. And again, I will introduce the building blocks here first, shortly, and then we will look in OPUS tab, or OPUS Suite. So we have a product variant, which is the base of the modeling elements, and then we create what's called systems. So the systems are the sort of like the items are the hardware, where the breakdown elements is used for principal description of the product breakdown. So a product variant is also, it's more of a theoretical description of the product that we are looking at, but we use the concept of a system when we talk about the thing that is out flying or driving or sailing. That's the system. And again, that's also something, it is two different things. The product variant is the description from a maintenance or theoretical perspective, while the system is the actual operational entity that we deploy. But they're always based on the product variants. So a system is defined out of the product variants. Okay, and here as we saw before lunch, we were creating operational sites where we can deploy the systems. But it's also possible to create what is called units, and it's, again, that's sort of an additional level in the description of the model. It is much like a station, but it's only used for operational purposes. And we can define system deployments for units as well. Okay, and next step is to define the actual operation. So how much are we going to fly with this helicopter? Whatever type of system we're modeling. And we do this with what's called a utilization. Utilization means how often we utilize, how much we are running or flying the system, and a profile. And we can give this per year, and we can also split it up in number of missions per year. So very simple example here. So let's say we have a utilization profile saying that we are planning to produce 250 flight hours each year. And here it's split up in 52 missions, so which means that we do, then of course that's once per week. So on average, this means that we would produce 4.8 flight hours per week, or for each mission. Okay, so, and this is, again, it's just the basic description of operations. It can be done in any level of detail, and we can see more of that later as well. But again, we move into OPUS 10 to see how to add this. Okay. I have to turn off the presentation here to be able to see this OPUS 10. There we go. Okay. So we have our stations, and we have we need to define our the deployment here. So first of all, we can look in this category called operations, which is here. We can look at the table called system. Here I had already defined a system. As I said, the system is the actual physical entity that is in operation, and it is defined from one of our product variants. In this case, we only have one variant of the helicopter, so that's the one that we have chosen. It's very strange that the description of the helicopter is an aircraft. Let's remove that. Anyway, next step is to add the system deployment. So the table here is called system deployment. This is where we connect the system to one of the station or units in this model, and so on. So if we take a look in this Excel file here, we see that we had 10 helicopters at the alpha base and 3 at the beta base. Okay, so we define helicopter and the alpha base, and we had 10. And for the beta base, we had 3 quantity per unit or station. So there's the quantity, that's the number of systems, and we connect the system to the station. And you see them up here in the support organization view. You see here, it says that the deployment is 10 helicopters at this station and 3 here. Next step is to define the number of hours or the actual utilization for those deployments. So a deployment is really just a number of systems at a specific station, but then the actual operations is described from a utilization profile. So we need to go to the table called utilization profile and create this profile. And according to the input data here in the spreadsheet, it says that we have 2 different profiles for the 2 different stations. So I copy those 2 identifiers here and paste them into OPUS here. So it's a profile for the alpha base and one for the beta base. And the utilization per year is 900 and 600 hours. Okay, and as you see here, so it's the unit is one per year, so it's the number of operating hours per year. And the default value is 8,760, which is, that's as many hours as there is in 1 year, which would mean that a constant operation, which is not very likely in the case of a helicopter, but for other types, maybe a radar system or something that might be up and running 24/7. Anyway, we can split this up also in number of missions per year. And for A base we had 100 and the beta base was 200. Okay. Last step is, of course, to connect those utilization profiles to the system deployment. So I go back to the table system deployment, and you see here we have the utilization profile identifier column. So I do, of course, the profile for alpha connected to the alpha stations, and same thing for beta. Okay, so that's really what we need to do here. Pretty simple. We just adding we had the system defined. We create the deployment of the systems, and we added the utilization profile as well. moving on here with the presentation. Again, same thing when it comes to the operations, that we can start simple and then gradually define. So there's a very simple basic mission operational profile, but it can be taken into any level of details when we start working with more detailed data and so on. Okay, but this means that we actually have finished all three parts here, both the RAM properties, as we started with. We built up the support organization, and now we've added the operational requirements. So this is really what we need as a basis for starting running the actually performance analysis. And so what happens when we do this? Well, let's say in this scenario we were supposed to evaluate the current logistics support solution. That means that we do already have current spares location. So meaning that we have a set of items here. So let's represent these items in the example here with those yellow, pink, and blue boxes here. So we have a set of items of different types at different stations. And what happens then when we run this analysis of a current situation means that we end up with 1 point on this cost effectiveness curve or graph here. A cost effectiveness graph is what we often refer to, and it's simply the x-axis is the cost, and then on the y-axis we are measuring the effectiveness in some way. And here we are looking at availability in this example, but it can be other types of measurement as well. So with this stock solution, we will end up somewhere in this graph. It comes with a cost, and it gives us some kind of availability, given all the other information that we have put into the model now. And this can, of course, be interpreted for the different operational sites and see what that means in terms of operations. Going into the sort of more world of simulation, we also get the dimension of time. So we can see that how the availability varies over time, not just as one single steady state value. If the performance varies over time, it means that a lot of other things can also vary over time. And so when we build a simulation model, we can also say that the system's operations, they can be defined with any variation over time. Same thing for a lot of other things in the model, like availability of resources, how we transport stuff. The failure rates can actually change over time as well. How many systems that are deployed, how long time it takes to perform the tasks, etc., etc. So there are many things that can change when we build a simulation model. So that means that, again, we're looking at availability here for a number of systems that are ready over time. So here, if we had cost on the x-axis in the previous graph, we now have time on the x-axis. So that means that we get a chance to understand both when, but also why the performance is varying. And then, of course, what can we do about it to improve it? So first of all, the green is the number of available systems. And then we can see the yellow part here that shows how many of those systems are on mission. And then the rest are obviously unavailable, which means that they are not ready to go into operation. So, and then we want to understand this red part. Why are we unavailable? And we can look at another graph, splitting up this red section into different colors. Here we have the red one showing how many systems that are expected to be awaiting spare parts. So they are stopped from operation because they're waiting for spare parts. The dark blue part here shows us how many systems that are in active repair, meaning that we're actually doing something on the system. They might be also stopped for other reasons, such as preventive maintenance or administrative delays or simply waiting for other resources. So This is a typical outcome from the simulation, showing us over time in what different, how many systems there are in the different states that we see here on the right. Okay, so interpreting the simulation results is sometimes it's a little bit of thinking or processing just to know what we're looking at. So I'll try to explain. So what we do when we perform a simulation is that we take this input and we draw random numbers and random numbers for the failures and all the other things that can happen. And then we try to do the missions that we have planned for. And in this case, we actually have a big fleet of systems here. It's 60 systems in total. So we start off with 60 systems, but as time goes, you see it varies a lot how many systems that are available or ready for other operations. So and then we do this. We draw when we say that we run a replication, and it means that we draw random numbers once. So we draw one random number for all those outcomes, and we see what happens. So that's the first replication, and then we do another replication, which is that's why we try to illustrate that it's two layers here. So we have two different replications, which gives somewhat similar, but of course also a little bit different results, because it's a new draw of random numbers. So this is how so-called Monte Carlo simulation works, that we draw the random numbers many times, then we combine the results and create an average value from all the replications. And if we do this enough number of replications, we'll get very good statistics for the results as well. And here, after 100 replication, the curve will smooth out a little bit, and then we get another result. And something that's important here is to also understand when we talk about replications and simulations, is that it is this average out of 100 separate replications. And then we can look at things like percentiles, which is like a confidence level. So we can say that 90%, for example, you can set this level as you wish, but you can say that, so how many, or what is the level where we can expect at least 90% of the replications to end up? And here we see it's the gray curve here showing us, so okay, with 90% sort of security or confidence, we will end up with this value. There are some results that will be better, but we know with 90% probability that we end up here. And there are some that will be worse, of course. So that's how we can look at as well, called percentiles, to understand the confidence of the results. Of course, we can always aggregate these results, not looking over time, but actually look at the total values instead. So here we look at some kind of average availability that's aggregated over both those replications and over time. So there are different results categories when we talk about the simulation results. So we have mission results. We can look at the performance on the requested mission profile. We can also look at system results, which are centered around the system performance. Then we can look at the stock results. So how does our stock of spare parts perform? How many do we have? How many back orders do we have, and so on. So over time, yeah. And of course, we can also look at item results, where we see the performance of individual parts here. We see the number of failures and number of shortages and so on. And at last, also we can look at resource results, so the performance of maintenance resources. But we'll see more of that later on. Now, I think it's time to run the first calculation here and actually look at the result side as well. Going back to OPUS 10, we said that we were going to analyze the current situation. So here's a table called stock allocation. Stock allocation means a set of spare parts at all the different stations in this model, and how many we have. And then we can analyze that in order to understand what will that give us, what kind of availability will that give us. So going to the Excel file again, we see, find it here. Here we see that this is the current stock that we have at the moment. So we have actually 3 spare parts of each of our 8 items. So I'm going to copy that and paste it into OPUS here, and also name this, give this, an allocation is a set of spare part sizes here. So like I call it current, I can call it whatever I want, but let's call it current, so it's a current stock. And then I also need to go to the control parameters table. There are some different input parameters here in OPUS 10, but what I want to do is that I don't want to run the initial type of a problem, but I want to perform an analysis of the current solution, the current stock that we have. So that means that we're not optimizing at this moment, we are only evaluating the current stock. And I also need to say the point number here, so I select the current point here. I could, of course, have some other suggestions that I want to evaluate as well, so that's why I can have multiple different points. One more thing here in the sort of control section of the input, there is a table called global parameters, where we can set things like the scenario length, or we can add interest rates if we want to do present value calculations and so on. Some of that stuff as well. But just to show you here, we're looking at a 5-year scenario. All right, so that's it. That was, now we have the input we need, hopefully, if I didn't miss something. So it means that it's time to actually perform the calculation, as I said. So up here is this little small calculator sign in the toolbar of OPUS here. And you see it says calculate. If I point it, I can also find it here under tools. There's also a calculator. There's a shortcut for it, etc. But that's how we go from input to output. So pressing this button will start the calculation, going through all the input data and also interpreting data and see if it's right. And as you see, it wasn't right. I forgot something. And it turns out that it's always good to make mistakes, because then you can explain. But here it says that in the form or table called task, there are warnings that I have not given any level identifiers for those 2 tasks that we added. And which means that we also end up with 2 errors down here, the red text at the bottom, which says unknown identifier, base and energy group. So first of all, I need to go to the task table. In the maintenance category, there's a task table, and I can keep still got this, we can read it. So you see here is something called a maintenance level, which defines where I can perform the maintenance. Since I forgot to add that, we also get a corresponding error. So the replacement of the parts can be done at the operational level. So I select the first level here, and then the repairing the item is done at the depot level. So up on the, it's very small now, but up on the green station up here at the depot. That's better, hopefully. And see here that we have some other. I can also double click. You saw how double click the arrow down here, which will take me to that row directly. That was obviously it's not called the engine group. That one, it's actually called items. So that was if you remember, we created a component group when we created all the items. We said that all those items belongs to a group called items. So, and why did we do that? Well, it was to be able to make a more compact model. And in this case, we wanted to specify the maintenance capability. I didn't talk too much about this because I didn't want to go into all the details, but anyway, so in this table, we say that at the central the central station, remove it here so we can make it bigger. Here, up here at the central station, I can perform the level 2 type of tasks on the items. And the L2 task, going back to the task table, was the repair of the item. So, so the repair of item can be done at the central, and then we also said that the replacement were done directly at the operational sites. A good way actually to test yourself also is to click one of the items in the tree here. So if I click the fan module, we will see some information about this one. So it says that can be corrected up here, the fan module, and it takes 730 hours. But there is still no replacement here, so I still missed something. Another error. Sometimes I use the calculate functionality to look for errors in the model because debugging a model because it helps me to show where the error is. So it says that it's an unknown identifier. It says base. So here I'm saying that I can perform the L1 task, which was the replacement, at something called base, but that identifier does not exist here. And why is that? Well, it's because I haven't created any group. If I had a station group, I can create it just like we did with the item groups. I could create a station group for those two bases. But if I can do it anyway, but I make it quick here. So I select, rather than creating a group, I just add the actual alpha and beta bases instead, like this. So the variant can be, on the variant, we can perform L1 tasks at the alpha and beta base. Now, let's try again. Hopefully it works better. So it asks if I want to save it and calculate. Yes, I do. And there we go. We get a point. And as I said, this was not an optimization in the true manner. It was an analysis of this current solution. So we end up with something that would give us, for this very simple model, but still very simple helicopter, but it would give us 98% availability, and the cost here for our scenario would be $39,000 or euros or whatever currency we're looking at, right? Now the big question is this acceptable from a readiness perspective? Well, of course that depends. Are we satisfied? Do we think this is good enough? What are the requirements? What are we expecting from those helicopters? What type of availability are we expecting? And also, of course, what does the cost mean? And well, in this case, it's not that we haven't added anything but the spares investment. So it's only investment in spares here. Okay. And then I also want to show you same case here, but we'll do some simulation on it as well. So looking at the simulation module here, again, we can open the same file. So I can select again the OPI file, so I know it's the same file that we were working on. And you see, it looks exactly the same here, still in Opus. It's the Opus Suite, it's the same files, it's the same interface, a little bit different. Here we can give some additional data since it's a simulation module, but otherwise you recognize everything, I think. And actually, we don't have to add so much more here. We have this very basic description of the operations that we gave in the, if you remember, we gave it in the in the system deployment, we said that we have the number of systems, and we gave those basic default profiles, saying that we're flying 900 respectively and 600 flight hours per year, split up between a number of missions as well. Okay, so hopefully we don't have to do much more here. Press the simulate button instead, and you saw it went so quick you didn't even notice, but what we did there was, here I go back to this progress window. You see that, okay, I run 100 replications. As I said before, one replication is one random draw of the failures and everything that is random in this scenario. It ran through very quick for those 100 replications. And then we formed the average values out of those 100 replications, and we got the result here. And as I said, here are a lot of results to look at, but in total, here you can see the mission results and select between different things here. Here is the total between over our units or stations. So if I uncheck here, we see the alpha base and the beta base, and we can calculate here the number of systems multiplied with number of operating hours per year, multiplied with 5 years, and somewhere ending up with those values. So much more operation at the alpha base. It's a total of 27,000 hours or something, and 5,500 or something here for the beta base. And again, the colors represent the different states and how it goes. So out of all those hours, we see that there are, hard to read, but for the alpha base, there is, over those 5 years, there will be 668 hours that we cannot fulfill. And for the other one, it's around 300 hours. I can also, of course, I can right click here, or we can look at things in percent instead if you want to. So maybe easier to compare two bases to each other. And maybe as expected, since we are operating more per year at the beta base, we see that we also lose more in percentage. We lose more of the time compared to the alpha one. We also remember that we had more. I always just have to check why there was so much more. We have a different number of systems as well. So, yeah. Anyways, yes. So that's one thing we can look at. For, as I said, in percentage, might be easier. But also, if going back to up here to this box where you can select the system results instead to look at more at the specific systems. So here we see what's called the system states. Now we have the time dimension on the x-axis. So 5 years is 2,600 hours something. We can change here to years if we think that's better. So time unit years will be easier. And okay, I had a profile for 3 years, sorry. So it's not 5 years, it's 3 years. Because the input is a little bit, that value of 5 years in OPUS 10 is not the same as the simulation period in the simulation. But anyway, I think you get it. So what happens here, we start out with 13 systems, 9 plus 10 plus 3, 10 at the alpha and 3 at the beta. So that's, of course, we have 13 systems here over time. And from the very beginning, all of them are green. That means they are ready to go out and perform. But as soon as we start to operate or fly with the helicopters, some of them will need maintenance. And you see that it drops pretty quick. And there are a couple of systems that are unavailable here. And some of them are ready and some of them are yellow, which means that they're actually on mission. But we're not utilizing that many systems at the time, so that's why we had pretty good mission results. So, and this is really the difference between system availability, which means something, And as we see here, how many systems are available, maybe not that many. And if we would make a total out of this, or actually we can do it like this instead, look at system availability and do that in percent. Press the wrong one. Okay, we see that, okay, so on average we're almost down at like a 50%, 60% availability. And that's maybe not so, that doesn't sound too good, but still we produce almost 100% of the mission time. So that's why it's important to understand the difference between mission requirements and the system requirements. We can also look at why we are unavailable here. Click here. You see there's something called system unavailability, so that will give us more details about this red section of the graph we're looking at. So we see here, almost all of it is due to that we are awaiting items. So we're having not enough or the wrong type of spare parts. And there are also, at the bottom, there is a little bit of blue here, as you see, not much, but that means that we are unavailable due to active repair, meaning that the systems are locked because we are removing and replacing items on the systems. But it's obvious that it's the spare part here that causes unavailability. And the last section that we can look at here is not there, but here we can look at item results, for example, and looking at stock levels here for the different items. Here it's split up between the different phases, but we can also, for example, look at the number of demands. So if you look at number of demands, I also only select our two operational stations, the alpha and beta. And we see for the alpha and beta base how the demands are aggregated. Here we're looking at total. We see that for the compressor plates we have 18 failures over this scenario, and for the beta base we have 3.4 failures because we have less systems there, so we will also get less failures. And then you can also, just to show you can play around with the results a lot here, so I can change the order of them, so I can compare the item by item, I can compare between the stations to see the difference as well. And of course, if you have multiple files, etc., you can just, it is pretty flexible here on how you can present your results. So there are a lot of different results to get, but the question is if can we get the answers we need? Well, I think so. And if we go back to OPUS 10, I just want to show you also that we can get some overall reliability data also in OPUS 10. So there is something called a result table. This is a result graph. It's the cost effectiveness graph. But we can also look in a result table here. So if I go there, and I'm just going to select some system results, and then I can also go and look at, let's see, scroll a little bit, this one. So I might want to look at the something here. So mean time between failure, for example, and because we only have other things I want to see. Mean time between failures, it's going to be the same anyway. So we see that this is not dependent on how many systems we have per station. It's a value for an individual system. So the mean time is between failure is 339 hours, given all the input that we had. So this kind of can also have, if there is a failure, you can look at the mean downtime. So for a failure, that is however different because that will depend on how many failures we get. Even though for a single system, the time between failure is the same, the mean downtime will be different because they sort of compete with other systems at this place. So looking at the different ones, we have 46 hours in downtime at the alpha phase and 54 at the beta phase. That's average values given the current stock solution. Yes, so let's do this in the right order there. I think we should do that here. Yes. So now could we answer the original question? Well, no one remembers the original question, so I say yes. But it was about what is the current situation? What can we expect from this logistics support solution that we have today with those spare parts that we have, with those repair times, with those transport times, and so on. We can get out a lot of results from the simulation, especially to understand this. And are the results satisfactory or not? Well, that depends on the requirements that we have at the moment, right? So what are next actions, next steps? Well, I think we're going to look at some more details and to see how we actually can improve here. So then the question is, let's assume that this situation that we just analyzed is not acceptable. So then, what are the best ways to improve this performance of the systems? Well, okay, based on the results from the analysis that we did, we can investigate possible ways to improve. So what can we improve then? Well, maybe we can improve the properties of the technical system. That's one way of doing it. So better reliability of the parts, for example, is one way. So that could be how. But if we have a current fleet, that might not be that easy to do that. So can we maybe improve the support concept instead? And if we are an operator of those helicopters, yeah, maybe we can invest more in either spare parts, or we can improve the transport or something like that. So there are different options around it. And question is, can we reduce the operations or lower the requirements from an operational perspective? Well, of course we can fly less with the helicopters, but we probably don't want to do that. And if we are the manufacturer, we don't want to go to the customer and say, hey, fly less. That's not going to be so popular. But anyway, all this comes down to how much can we change those things, what will the effect be, and what will be the cost. So we did this analysis, as you recall. We said that we have items A, B, and C. We have X, Y, and Z of those in the store. So that gave us 1 point on the cost effectiveness growth. And again, that could have been split up for the different stations as we were looking at, but it was no optimization. So what we rather want to do is to see if we can, first of all, maybe we can see if it's possible to reallocate those spares in some way. That's one way of doing it. So maybe we can increase the performance by reallocating the spares that we have. Maybe we can rearrange them. So as you see in the picture here, we move around a little bit. So we borrow one from one store and put it in another one to make the solution better. So that's called a reallocation. So that means that we're not buying any additional spares, but we can actually see if it's possible to get better with the stock that we have. And maybe that will give us some increased performance. The other way is to look at what we have and then maybe spend some more money on buying more spares. So if we add more spares here, we can also get additional points. And of course, we're going to move to the right. And I tend to point with my mouse on my screen, but no one sees that. So sorry. Anyway, we were here. We went up a little bit if we did this reallocation. And then, so if we invest more, we can add new points to this graph here going upwards. Of course, we will move to the right because it will cost us money. So the cost will be higher if we invest in more spares. So the point will move to the right. But if we do this the right way, the availability will increase also. So the point will also move upwards. And this is what the optimization is all about. Do this in the best way. How can we move? We want to move as steep as possible on this curve. Of course, we want to move straight up. We don't want to pay anything more. We just want to increase the availability. But that's often not possible. So we probably have to take some additional costs or investments here in order to move up and increase the availability. And here is what doing these things is what the optimization will help us to do, to increase the availability with additional spare parts. And this can also be done of course, we can do it from scratch, starting down at this point down here, which is 0, and that's so we have no investments or no existing stock, and that's typically what you do in early phases or in initial provisioning, etc. But for this scenario, we said that we already have this fleet, we already have this stock existing. So that's why we started from a starting point here. Okay, another thing we could do to try to improve is to look at the transportation. Maybe today we are using trucks which are pretty slow, which takes a long time, which ultimately will decrease the availability because the systems are waiting for having spare parts delivered. If we can go for some other type of faster transportations, we will probably also be able to increase the availability. But again, this will also come with a cost probably, and if so, we need to analyze if it is an efficient solution or not. Another thing could be to think about where can we stock our items. We're talking about stock policies. So here, sort of as we have now, we have one depot where we have all the all the spares. But maybe we can invest in some local storage, so we get to another level here. So it means that we can have spare parts at other locations too, which might be able to increase the results as well. So let's look at some of those alternatives, because this is as engineers or as analysts, this is what we want to do. We want to try to provide good solutions, good ways to move forward in order to control and increase the performance.
그다음에 툴이 지금 현재 국내에서 많이 쓰고 있는 게 이제 3가지 모듈이잖아요. 오퍼스텔, 그다음에 심럭스, 그다음에 마지막에 퀴터나게고. 오퍼스텔은 군수 계획 초기 단계에서 설정했던 모델을 베리파이 하는 거다 이렇게 생각하시면 됩니다. 베리피케이션이죠, 일종의. 그다음에 실제 그게 베리파이가 됐다면 어떻게 우리가 밸리데이션을 시켜야 되느냐. 그럼 다양한 상황들이 나와야 되거든요. 다양한 상황들에 대해서 밸리데이션 시키는 게 일종의 시뮬레이션 기법이고, 그게 심덕스다 이렇게 이해하시면 될 것 같습니다. 둘 다 우리가 군수 지원 계획에 대해서 수립을 할 때 항상 돈이 문제거든요. 그래서 그 돈에 관한 요소들을 어떻게 우리가 산출을 해야 되느냐는 그 캐틀락이 이제 마지막에 하는 건데, 따라서 캐틀락은 뭐예요? 오퍼스텝에서 했던 내용들을 그대로 돈으로 환산하는 거고, 심덕스도 마찬가지고, 심덕에서 했던 것도 마찬가지고, 바로 연결이 돼서 돈으로 환산을 하는 작업들을 일단 해준다. 따라서 셋 다 데이터가 다 공유가 돼요. 왔다 갔다 이렇게 할 수 있고. 그러다 보니까 이제 디테일한 오퍼레이션에 대해서는 상당히 이제 많은 교육이 필요한데 그런 과정들이 별로 없다 보니까 제가 그냥 대전하고 서울에서 소규모로 한 10명 이내로 모아가지고 계속 교육을 진행하고 있습니다. 그래서 연락을 따로 주시면 될 것 같고요. 그 다음에 지금 제가 교육 자료를 요번 주에 받아서 제가 아는 수준까지 쫙 한번 읽어봤거든요. 스텝 바이 스텝은 되게 잘 설명을 하고 있습니다. 그래서 여기 이제 디테일하게 들어가서 해야 되는 것들에 대해서는 오늘 뭐 질문을 해주시거나 아니면 제가 뒤에 앉아 있거든요. 뭐 저한테 말씀해 주시면 이분들한테 질문을 해가지고 문제점 있는 것들은 해결하고 가실 수 있도록 진행을 하겠습니다. 오케이?
Yeah.